This quick presentation is going to be over chemical equations. It's kind of a continuation of counting atoms. The only difference is that chemical equations are kind of a bigger picture of why we need to count atoms. So, as a quick review, chemical reactions are changes that occur when atoms rearrange themselves. So when a chemical reaction or a chemical change occurs, basically we're taking certain substances and combining them with other substances, and something's going to change to make a new thing. So certain chemical reactions can absorb or release heat, light, and sound, and that's going to be an indicator of that chemical change. With any chemical reaction that there is in existence, there has to be a way to represent what goes on in that reaction. So for example, when you combine vinegar and baking soda, there's an equation that goes along with that reaction that shows you, vinegar and baking soda combine and they react to make blah, 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 blah. One of the products is carbon dioxide. So chemical equations are used to describe what goes on in a chemical reaction. So what is an equation? Skip it. Chemical equations describe a reaction. So here's a reaction for you. Here we have carbon found in charcoal, and that combines with oxygen in the air, and that creates CO2, carbon dioxide. So how do we know that that reaction happens? Well, when we're done with this reaction, the carbon is no longer there. And when we're done with this reaction, we're left with smoke and we're left with ash. So it's CO2 that we're seeing. So this is just a way to represent what goes on when you actually burn charcoal in a grill. So parts of a chemical equation, there are really three parts. The left side of the arrow is referred to as the reactants, and that's pretty much what you start with. So in that previous reaction, we had charcoal and we had air. In order to make this reaction happen, you have to have both of those. You have to have charcoal and you have to have air. If you run out of charcoal, suddenly the reaction stops. If you run out of air, for some reason you smother the fire. Maybe you take a fire extinguisher and you hose it down with CO2. Well, it no longer has this oxygen, so it can't react anymore. So that's kind of like how we put out a fire. You can smother it using a fire blanket, use a fire extinguisher, you can stomp out a fire. So there's a lot of different ways you can go about trying to stop a burning or combustion reaction. So the reactants are what we start with. The things that we use to make the reaction happen. And on the right side of the arrow we have the product, CO2. And that's kind of what the substance or molecules that are formed in the reaction, our products. What do we end up with as a result of that chemical reaction? And in the middle we have our arrow, and that arrow is just read as yields. So if you were to read this whole thing out loud, it'd be carbon, or C, plus oxygen, or O2, yield, carbon dioxide, CO2. So carbon plus oxygen react to yield carbon dioxide. This is just some independent practice. We will get plenty of practice with naming the elements, reactants, and products in class, so don't worry about this. The reason why chemical equations and being able to count atoms is important is because of this law, the law of conservation of mass. It's not like a U.S. law, it's like a universal law that applies to every known object, every known mass in our universe. It states that matter cannot be created or destroyed, although it may be rearranged. We talk about the rearrangement of matter as being chemical reactions. But the main thing here is you cannot create, you cannot destroy matter. It's not possible. So because the law of conservation of mass, chemical equations must be balanced. They must have the same number of each element on both sides of the equation. So what we start with, the atoms, is the same as the number of atoms you end up with. That's important. You can't add atoms because that means you created matter. And you can't lose atoms because that means you've destroyed matter. You can't do that. So a chemical equation must have the same number of elements and atoms on both sides of the arrow in order to be balanced. So taking a look at this equation, here we have 2H2, 2 molecules of hydrogen, so that's a total of 4 hydrogens. We got 1 molecule of O2 or oxygen, and that makes 2 molecules of H2O, 2 molecules of water. So the way that I would normally have you guys go about balancing this equation, or checking to see if it's balanced or not, is simply by drawing a T-chart and comparing the reactants, the left side, and the products on the right. So what elements do you have? You've got hydrogen and oxygen on both sides, H and O. And we just simply see how many we have. For hydrogen, we have 2 molecules that each have 2 atoms of hydrogen, so that'll be 2 times 2 is 4. Over here on the product side, we've got 2 atoms times 2 molecules, so 2 times 2 is 4. With oxygen, we've got 2 here, and we've got 1 here, but we've got 2 molecules, so that's 2. So 2, 2 for oxygen. And so it just shows you very briefly how to do that. What operation do we do to get this 4? Coefficient times subscript. For oxygen, it's just a subscript. There is no coefficient, so we assume it's 1. Again, same thing on the other side. Coefficient times subscript. Coefficient times, there is no subscript for O, so it's just 1. 2 times 1 is 2. So a chemical equation must have the same type and amount of atoms on either side of the arrow in order to be balanced. So this equation, since it is 4 hydrogen that we started with, 4 hydrogen we ended up with, 2 oxygen we start with, 2 oxygen we end up with, we know that this equation then is balanced. Here's another example of what elements you have. You've got 1 aluminum here, you've got 2 aluminums on the product side, so it's very easy to see that this equation is not balanced. Here we have 2 bromines, product side we have 6. Again, this is an unbalanced equation. It doesn't take a whole lot of effort to figure that out. So since the numbers are not the same, what this indicates is that we started with only 1 aluminum atom, and after the reaction we had 2. Well, that means you made matter. That can't happen. Over here on bromine, we've got 2 that we start with, and we end up with 6. Again, we made bromine atoms. You can't have that happen. You cannot make matter. So this is an unbalanced equation. So what would happen, or what would be kind of the next step, is you would have to go then and actually balance this equation. It would actually take 2 aluminums to make this reaction happen. So 2 would be our coefficient here, and you'd have to have 3 bromine molecules in order to make 3 times 2, 6 bromines. Just another practice. We'll get lots of practice with this in class. Reactants, we got 3 potassiums, 1 phosphorus, 4 oxygens, and 2 hydrogens, and 2 chlorines, and we end up with 2 potassium, 1 phosphorus, 4 oxygen, 3 hydrogen, 2 chlorine. So because the potassium and the hydrogen are not the same, we started with 3, and we only ended up with 2 potassiums. Technically that means that we're saying we destroyed matter. We can't do that. This equation is unbalanced. With the hydrogens, we start with 2, we end up with 3, so technically that means you made matter. You cannot do that because of the law of conservation of mass. So if you need help with balancing equations or you need extra practice, I hope that you come see me during tutorials. I can offer you some additional help beyond just what was in the PowerPoint. Otherwise, I hope this was helpful for you, and have a good day.